Save big this summer with great deals, all in the Baker's app. Get red, green, or black juicy seedless grapes for $1.88 per pound with a digital coupon. Then buy 2, get 2 free delicious 12-packs of Coca-Cola, Pepsi, or 7-Up, all with your card. Shop these deals at your local Baker's, less than 10 miles away. Or tap the screen now to download the Baker's app to save big today. Baker's, fresh for everyone. Prices and product availability subject to change. Restrictions apply. See site for details.
People very often ask me both how and why I started my podcasting journey. Well, as an engineer, I'm frankly very passionate about math. I wanted to find somewhere to share stories of great mathematicians from Archimedes to Alan Turing and everyone in between. And for that reason, I want to tell you a little bit about my preferred hosting platform, which is Zencastr. Now, before I continue, this is usually the conversation I have with anybody who is wanting to start their own podcast. I know there are so many people out there with passions that they want to share with the world or unique knowledge that they're just looking for a platform to start with. And Zencastr is a wonderful all-in-one platform. What I mean by that is you can do your recording and your editing and use AI to create a transcript and distribute to all platforms, including Apple Podcasts or Spotify or anywhere else where podcasts are played. For anybody like me who might worry at first about what you might sound like on an audio recording, Zencastr's post-production process makes you sound really, really smooth. It automatically removes any of the ums or ahs in your recording. It removes any of the awkward pauses in conversations, and it also helps you to set the right podcast loudness and levels while reducing any background noise, all with the click of a button. It couldn't be easier. Go to zencastr.com/pricing and use my code BREAKINGMATH, and you'll get 30% off your first month in any Zencastr paid plan. I want you to have the same easy experience I do for all my podcasting and content needs. It's time to share your story.
Before we start this episode, we have a little bit of news about the Planck constant. It's been redefined. It will be in 2019, but the decision was made this November 2018. Do you guys have any thoughts on that?
That's pretty significant. That's going to change a lot of things, isn't it?
Well, I mean, it's going to make things more accurate so that everybody can agree on a value. But basically now the kilogram, the second, all SI units are in terms of numbers and things that you can find anywhere in the universe.
Is that why they decided to redefine it, just so that it would be standard?
Yeah, they've always been trying to redefine it. Like in the beginning, a meter was defined in terms of the world. It was 1/10,000,000th of the distance between the poles.
We may have fudged it a little bit, but don't,
everything was based on unit, on things that you could find in specific places. And one by one, they've been going away. And now we have all the units in a way that you can find anywhere.
So real quick, what did they use? Because actually, full disclosure, no, I did not read the article. I knew about it, but I didn't read it. What did they use to come up with the new Planck constant?
From what I could tell, they used it was something like they made a sphere with the same weight as it. I'm not sure exactly. I haven't read all the things about it. I'm sure we'll learn more about it from the general press as time goes on. But they essentially counted the number of atoms. They're also redefining the Avogadro constant, the number of atoms in a mole.
Oh, wow.
It's interesting to me that we're updating our measurement system for a changing view of the universe. So it used to be totally based on just the Earth, and now we're basing our measurement system on the whole universe.
Yeah, it's pretty cool. I mean, it's still based on the original artifacts, but...
Yeah. I wonder how things will change then. Once this is done, how much more precise can you go,
Yeah, well, I mean, with this, you could literally be as precise as you possibly can be. There's no more precision that you can get from units, but I know that there's this scale that they're developing. It's so accurate that they measure the falling. They measure the local gravitational constant in the laboratory by dropping something and looking at the interference pattern from a laser.
Oh, wow.
And then they oscillate the matter back and forth and measure the amount of energy it takes to keep it oscillating.
As you say, this is a bit of a side topic. When you talk about precision, I think that a good conversation on precision would be a great way to combat fake news, especially when it comes to topics like climate change, when you actually talk about the precision. You know what I mean?
Oh, definitely. Precision is everything in science. It's the end. I mean, there's reasons why metrologists have been getting better and better at this kind of stuff. They have really insane kind of stuff that they're doing.
Yeah, things weren't always precise, but obviously we've improved it. So, good topic.
Yeah, and so just real quick, the second is defined. We'll do all the SI units right here. You can skip forward probably about 45 seconds if you want to. But a second is the duration of 9,192,631,770 periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. I don't know what a lot of that means.
Okay, yeah. Wow,
That's intense.
That was a lot.
The meter is defined by how much light travels in 1,299,790,458th of a second. So the meter is determined by the second.
Interesting.
The ampere is defined by taking the elementary charge to be 1.602176634 times 10 to the negative 19th coulombs. The kilogram is defined now in terms of the Planck constant, the meter, and the second. The Boltzmann constant is defined as 1.380649 times 10 to the negative 23rd joules per Kelvin. The Kelvin is defined in terms of the other units. A mole is now exactly 6.022140076 times 10 to the 23rd things. And the candela is measured as in a given direction of a source that emits monochromatic radiation of a frequency of 5.4 times 10 to the 14 hertz and has a radiant intensity in that direction of 1/684th of a watt per steradian. So all the units are dependent on one another now, and future space colonists, just listen to our podcast.
That's interesting. So, like, when you say they redefined, like, the constant and the measurements, like, it's like they took the old measurements, but they defined them with more precision, like Gabriel was saying?
Yeah, they're all plus or minus a few, like, 0.000s, but now they're perfectly the same. And what that means is that because the kilogram basically was getting old, it had gained about 20 micrograms in 300 years or so, which is too much for metrologists to handle. And now, onto our grave episode. Math is the gravely serious topic which has been traditionally done by stodgy people behind closed doors, and it cannot be ever taken lightly. Those who have fun with mathematics mock science, medicine, and the foundation of engineering. That is why on today's podcast, we are going to have absolutely no fun with mathematics. There will not be a single point at which you consider yourself charmed. There will not be a single thing you'll want to tell anyone for the sake of enjoyment. And there will be no tolerance for your specific brand of foolishness. And that means you, Kevin. Episode 36 of Breaking Math, the most boring episode ever. I'm Baca.
And I'm Gabriel.
And today we have on Adam Corlova. He's a friend of the show. He's been on, I think, episode 3, was it?
Yeah, I think so.
Yeah, and welcome to the show.
Hi, guys.
How you doing, Adam? Good to have you.
Now, before we get started with our serious episode, we have an ad for a serious poster about tensors, which are used in the serious theory. We have to stop with the serious stuff.
Yeah.
Of general relativity.
Yeah, this is an update. This is something you have not heard before. We actually have a price change.
Yeah, we got a better printer. Well, a different printer. Well, actually, it was the same printer, wasn't it? They just did a different process.
Yeah, they're able to more bang for our buck, so we can actually lower our prices.
And now our posters are pi to the e dollars each. And for you plebes, that's $22.46.
That's right. So that's not quite e to the I pi, but if you were to, it's not inverted. What do you say when you swap it out? You swap the two elements of a power.
Wait, if they're just multiplying by one another, wouldn't it just be the same power?
So no. So I'm relating the price of the poster to Euler's awesome proof.
I guess if you took -1, raised it to the ith power,
Yeah.
and negated it, you'd get our price of the poster. I don't know. That might be the case, but I think that is.
Yeah. So we'll say that price again. In terms of dollars, it is exactly pi to the e dollars.
And that's $22.46. You can get that through our Patreon, and it used to be $35, and that's patreon.com/breakingmath. And all you have to do is donate one time, and you'll get a poster.
Yep. Yeah. And I know it'll say, do you want this to be a recurring thing? No, we don't. Just one time is fine.
Yeah. And so...
Oh, and shipping. We now have a garage full of posters. So the shipping in the United States takes a couple of days. That's it.
Yeah, and of course, shipping around the world, because of restrictions and all that kind of thing, we're going to have to still charge shipping for international orders, but it is still available internationally. A couple of announcements. We've moved from SoundCloud to Anchor now.
That's right. Anchor is a newer platform for podcasters. And our new address is anchor.fm/Breaking Math Podcast.
But of course, you'll still be able to pretty much seamlessly get you're listening to us now. You'll be able to get our stuff from anywhere, unless you were listening directly on SoundCloud, but very few people were.
Mm-hmm. Absolutely. So any source that you previously heard us, we are still available on Apple Podcasts, Google Podcasts, which is actually a newer one, Stitcher, all of them.
And Gabriel, you're launching a new podcast?
That's right. Actually, it's not just me. It's Santa Fe Trail Media, which is the name that we use for all of our podcasts. It's the whole umbrella. Santa Fe Trail Media will include the Breaking Math podcast and every other venture. Our brand new podcast I'm so excited about. Once again, we have reached out to educators. We have found a teacher with which to launch a new podcast. This is a speech and debate podcast, and we are so excited. The host is a gentleman by the name of Trey Smith, who has been involved in speech and debate for over 20 years. He started a speech and debate club at a very small charter school, and in very short order, I believe 3 years, they dethroned the 24-year reigning champions, or was it 23-year? They dethroned the local champions, and they're very successful. The podcast name is The Soapbox with Trey Smith. You can find it on Facebook. You can also find it on Anchor at anchor.fm/The Soapbox Pod. And it's real exciting. It's all about stories from speech and debate. It's about how you build an argument, how you communicate. There are stories of debilitating defeats and really amazing victories. So hope you find it on anchor.fm and enjoy it. Let us know what you think.
And of course, our episode today, we're going to drop the pretense. It's about recreational math.
Yeah. The original title, full disclosure, was Fun with Math. We just sort of went the other way with our theme there.
Yeah, and as you heard from our new theme, we had to use that. So, Adam, what experience have you had with recreational math, and how has it affected you?
That's an interesting question. Like, I went through math through 12th grade and then into college. And then I left college for a few years, and before I left, I really did not enjoy math. I had been through, year by year, through high school, and I didn't have the best teachers, and it was just like doing my math homework was not something that I wanted to do ever. It was my least favorite homework of all. But now since I've returned to college, I went back and started in earlier algebra and worked my way back through, and now I'm on trigonometry, and so I went back through a lot of math just to make sure that I had a solid foundation, and I'm really enjoying it now. I'm finding that actually I look forward to doing my math homework now. I look forward to doing a test. It feels good to get a problem right. You get a little bit of a rush from that, especially a hard problem.
Yeah, and I think that's kind of the driving force behind recreational math. Is that humans are like crows. We love new stimulus.
Definitely.
And as soon as we can get new stimulus, we get this irrational. It is irrational because there's no rational end to anything in a certain sense. But just having this reaction to discovering new things has seemed to help us very much over the centuries in millennia.
Yeah, absolutely. Yeah, goodness. I may take a stab at the same question, if I may. On recreational math. So I think, as a young student, in elementary school, I had a lot of teachers who were very good at it. A lot of fun math games. They made a game out of everything, including things like how quickly can you do your times tables. But it's not just that. I think in our nation's history, there are several examples of very stimulating mathematical columns in newspapers that include puzzles. I think Stephen Strogatz is one of the authors who does a lot of great puzzles.
I'm not sure, but one thing that you did, I just have to bring up because you mentioned our nation's history, is that President Garfield has a proof of the Pythagorean theorem.
President Garfield?
Yeah.
Really? Oh, wow. Huh. Fascinating. Yeah. So there's there's certainly an enjoyable aspect to it. It's the same way as puzzles. I am going to include, games of Tetris where you have to strategize how you, fit things in. So it's really not difficult to talk about mathematical, games as just a topic of pure enjoyment.
Yeah, but as far as you were mentioning, you were helped by recreational math during a job interview.
Yes, I really look forward to sharing this story. I actually landed a job thanks to recreational math. Now, there's more to the story than just that. Essentially, I was interviewing a while back for a job that was essentially an entry-level engineering job right out of school. I was fairly excited about it, and I sat down with the interviewer, and he told me, full disclosure, during this interview, I have a few mathematical puzzles that I'm going to give to you to solve, and I'm very interested in how you go about solving them. That is very important information for me, and I think that it helps me to assess whether or not we're a good match. So I was like, oh, okay. I got a little bit nervous, and he gave me a couple of puzzles, and I'm going to share two of them with you all. The first puzzle he gave me was what do you call them? One of the blacksmith puzzles.
Yeah, I think that's what they're called.
Okay.
The iron puzzles that are in squiggly shapes, and the goal is to separate the pieces.
Yes, the goal is to separate the pieces. And this particular puzzle was it had like a long, thick screw with a bolt on one end, and the bolt looked like it had been soldered. It was like a real sloppy solder job. That was just like, I don't know how to describe it. It looked like
It was bumpy.
Yeah, bumpy, and it was like melted ice cream. Like, it was all over the place. It was like they didn't do a very good job. So on the other end of it, so the other end of it was a hook, and it was not a straight hook. The end of it was slightly bent to the right, so it looked like if and I also didn't mention, there was a ring that was attached to the hook, and the idea was to remove the ring from the end of the hook. And, based on how it was bent, I was sure that there was some way that I could orient that ring in order to pull it off. So, during the interview, I'm telling them all about my experience in college and all of my engineering projects and all this stuff, and I'm trying to bend this thing and undo it. He kept asking me if I would like a hint or if I'd like any help, and I thought, this is an interview, this is a test. My answer was no, thank you. I'd like to do it myself, which is what I thought he wanted to hear. I kept going, and during the entire interview, I didn't get it. He then finally stopped me and said, the reason why I asked you if you wanted some help is I wanted to see how, if you got frustrated, would you ask for help? And at the time I was like, oh, I thought did I blow it? And then how I recovered from that is I told him, I certainly plan to ask for help. I just believe in exhausting all my options first before asking. I'm not opposed to it. I hoped that I could show that I was a hard worker or something. Now, this kind of went on back and forth, and then finally I said, in the interest of this interview, I'm going to stop myself and say that I will accept your help. And then he said that he took the puzzle from me, and he said, when you have tried everything that you think it could be, and it doesn't work, it has to be something that is impossible. He then took the end where the screw was welded shut, and he just turned it and unscrewed it. It was a fake weld. It wasn't welded at all. And then he just took the ring off that way. So, yes, I was completely duped. I didn't even think to try that.
It reminds me of that. There's a puzzle in the show Star Trek, the Kabayashi Maru, that's supposed to be it's an impossible to solve task.
Okay.
And it just kind of reminds me of the same thing. But what is interesting is that you must have had an enjoyment for recreational puzzles to have had the muscles in your mind to keep going at this, like, very frustrating. I've done these tasks and they're frustrating.
Yeah. Well, and also I've learned something. From now on, anytime there's a puzzle happening, I'm not going to rule out ridiculous things, because it is possible. It is very possible that the person giving you the puzzle is, trying to just trick you, and that's all there is to it, which was the case here.
Game theory.
Yeah. Now, he gave me another puzzle as well. This one was I was real excited. The other puzzle he gave me, I solved in 30 seconds because it was very similar to something that we had done on a previous episode. So my research that had gone into the Breaking Math podcast had really worked in my favor here. I'll go ahead and share this puzzle. It's a prisoner hat puzzle. So in this next puzzle, according to the story I was told, there are 4 prisoners who are arrested for a crime, but the jail is full and the jailer has nowhere to put them. So he eventually comes up with a solution of giving them a puzzle so that if they succeed, they can go free, but if they fail, they are executed. That sounds pretty intense. So essentially, in this puzzle, you all may have heard it before. The jailer sits 3 men in a line. Let's just call them A, B, C, and D. B faces a wall. C faces B. D faces C. And then there's B, of course. Now, the 4th man is put behind...
Wait, hold up. So what regiment are they in? B faces the wall. Which wall?
Sure. Let's see here. So B faces the wall. C faces B.
Okay, so B is facing the wall and C is looking at him.
So the reason why I mentioned that is that B cannot see anything right now.
Okay.
Yeah.
Okay, so B can't see anything. Yep. C can see B.
Yes, that's correct. And
but no one else.
Yeah, okay. D faces C. Oh, yeah. The other thing is D, the last prisoner, the 4th prisoner, faces C and B. So he's got a little bit of a leg up. The 4th man, A, is put behind a screen or in a separate room, perhaps. The jailer gives all 4 men party hats. He explains that there are black hats. He explains that there are 2 black hats and 2 white hats. That each prisoner, each prisoner is wearing one of the hats, and that each of the prisoners sees only the hats that are in front of them, but neither on themselves or the one behind them. Now, the 4th man behind the screen can't see or be seen by any of the other prisoners. No communication among the prisoners is allowed. So if any prisoner can figure out what color hat he has on his own head with 100% certainty without guessing and tell the jailer, all 4 prisoners go free. If any prisoner suggests an incorrect answer, all 4 prisoners are executed.
So it's a double-pronged problem where you have to figure out who knows and who know and how they know.
Yes, absolutely.
And they can't communicate with A.
Yes. The puzzle is to find out how the prisoners escaped. Now, here's what I did, and what I'm going to let you all do as listeners and for you, my co-hosts. What I did is I began strategizing and thinking aloud, and I just told him what I would do. I basically I wrote down all the information he gave me, and then I categorized it. Now, without telling you how I did that, what do you guys think? What would you do?
I would probably do something like draw a tree of all the different possibilities, something like that.
Yeah.
This is kind of funny because my math teacher this semester actually started our class with a version of this problem.
Okay.
And it completely stumped me. But the thing that I did do was draw a picture first because I tend to be really visual with stuff like that.
Exactly. Now, what I did is in problems like this, I think before we did the Breaking Math podcast, I didn't think very carefully about it, and I didn't look for hidden clues. There's some hidden clues here that are only apparent when you diagram every single bit of information. So just ask yourself, what is every single thing that we know, and what do we know about what the prisoners know? Should we, I don't know, should I give the solution now?
I think that we should give it on next episode.
Okay, absolutely. So on the next episode, now don't cheat. We will give the solution to the prisoner hat problem on the next episode.
Oh, and yeah, speaking of episodes and things like that, a quick thing. I said that I can't remember which episode it was. I said that Omar Khayyam helped to transcribe the 1001 Nights. I was mistaken. It was actually a test that I studied for in 9th grade. It was a mnemonic device that I was taught that he had something to do with it. So I literally I remember the song that I sang. I'm not going to sing it for you guys, but anyway, sorry, I gave you guys bad information.
That's quite right. Yeah. And thank you for our listeners for pointing out when we have inaccuracies so that we can correct them. We do our best, but sometimes things slip through the cracks, and we appreciate your feedback.
So we're going to talk real quick about Ramanujan and the taxicab numbers. And I think this is a good story just because it's just about pure recreational mathematics and a very famous mathematician. So this one is a really simple story. Ramanujan and some mathematician were in a taxi cab, and Ramanujan is really well known for a lot of really incredible mathematics, a lot of things like nested radicals, like square root of 1 plus square root of 2 plus square root of 3 plus square root of 4 plus, but like not the square root of each number, like square root of, anyway, you keep really weird like things like that. He's good at that kind of thing, or he was in the 1910s. But they were in a taxi cab, and the number of the taxi cab was 1729. And the mathematician with Ramanujan said it was a really boring number. And Ramanujan is like, no, it isn't. It's the smallest number expressible in more than one way as the sum of 2 cubes. And he's like, you could say it's 12 cubed plus 1 cubed, or 9 cubed plus 10 cubed.
Interesting.
Yeah, that's crazy.
You
Yeah,
just like came up with that.
yeah, like instantly.
That's incredible.
Yeah, and it just goes to show, like, these mathematicians, they're in a taxi cab. They weren't doing other things, but like I don't know, they had no goal in mind, but mathematics still was something that they decided to do, and to the point where they called these numbers the taxi cab numbers from then on, numbers that are expressible in more than one way as the sum of two different cubes.
Wow.
That's interesting.
Can you imagine if you're the kind of person who just like went around and every single number that showed up, whether it was the amount of peas on your plate or whatever, you figured out the significance of that number?
Man.
I mean, you could do something kind of like this, I mean, I'm sure Ramanujan wouldn't have been lucky on every single number.
Yes.
But like if you're driving down the road, try to find patterns in the numbers and letters in the different things. When somebody rings you up at the checkout counter, try to think of the fastest way to remember that number forever.
It's actually really good. I know that there's a lot of memory mnemonic. That's one way of a mnemonic device is anytime you have to have a list of numbers, just think of patterns or stories to sort of anchor it to. Now, that actually would be a good idea. Numeric scavenger hunts. I don't know if you want to keep your kid busy for a while. Just like give him like a list of 14 numbers that are like 4 digits and say, find something that these describe.
Yeah, I mean, it's just a really simple way. I mean, it has everything that a recreational math problem has. It has a problem, which is just data. It has a solution that's non-trivial. It has the feeling of accomplishment. It's pretty much, yeah, it has everything you need.
I feel like the way I described that was so lazy and almost mean. Like, here, kid, just go figure out something significant about these numbers. Knock yourself out. And then, lo and behold, you've got a math genius who then tells you something amazing. So,
Right.
there's other ways to keep yourself occupied. But, yeah, the goal here is to do it with math.
Ramanujan is really interesting to me because apparently he believed that he was receiving his proofs from the goddess Lakshmi, which was his ancestral goddess, like the goddess of prosperity and beauty in the Hindu religion.
Yeah, he attributed a lot of his mathematical discoveries to her. That's another aspect of this kind of math, is that math has an emotional component as well as a useful component. If you're just pure boringness, then we wouldn't have, like, I don't know, we wouldn't have the festive notation. That's the dorkiest thing I've ever said. But we wouldn't have different stuff like that to go along with mathematics. It would just be a purely boring thing like accounting.
There's nothing purer than seeing somebody just raptured by the joy of mathematics and of counting things. I mean, think of the count from Sesame Street. 1, 2, I was just saying. I'm not being sarcastic. Not at all.
No, the count is a very important figure, both politically and economically.
We should have the count as a special correspondent on some news program on economics or something.
Is the count a vampire?
I think that's implied. We're not going to get sued by HBO now. They own Sesame Street, are they? On this next segment, the Towers of Hanoi, I'm going to read this segment here. First, you take 3 dowels and set them upright, left to right. Next, you place a series of cylinders with holes in the middle on the dowel farthest to your left, each smaller than the other so that they make some sort of cone shape when taken together. The goal of the Towers of Hanoi puzzle is to move every cylinder from that dowel down to the dowel on the right without ever setting a larger cylinder on a smaller one. I think my son has a game of this. It's like these like red and yellow and green rings, right? You know what I mean?
Yeah, they're like rings that you put on a peg, and you have to move. But the thing is, with this rule, is that you can never put a larger peg on a smaller one.
Okay, so the first strategy that I take here is sorting, obviously.
Well, not necessarily sorting, because there are only 3 dowels.
Okay, I was wrong.
So, well, kind of. Well, I mean, I don't.
I was wrong about being wrong. Sorry.
But it's. I mean, I know the solution to this because I was taught it in a class.
Okay.
But I would like to. I don't know. Discuss it.
Sure. Okay. So, now I'm thinking about my son here. My son is looking at these 3 dowels and these colors, and then I don't know that he's really strategizing at that time yet, but he could be.
Hold on 1 second. I'm going to do. We're going to do a quick cut, and I'm going to get some breaking math equipment. Hold on. And we're back. So right now in front of Gabriel and Adam, there are 4 cups, each smaller than the other, stacked within one another.
Okay.
Okay. Yeah.
Now, keep the cups together for now.
Okay, got it.
Now, put 2 mats so that you have 3...
At the UPS Store, we know things can get busy this upcoming holiday. You can count on us to be open and ready to help with any packing and shipping or anything else you might need.
Is there anything you can't do?
Actually, I don't have a good singing voice. The UPS... Nope. But our certified packing experts can pack and ship just about anything.
At least that's good.
The UPS Store. Be unstoppable. Most locations are independently owned. Product, services, pricing, and hours of operation may vary. See Center for details. Come in today to get your holiday goodies there on time.
3 places where you can put the cups.
Sure. Okay, so let me identify 3 places. Can we do in front of this?
And while they're doing that, I'm going to just explain the altered version of Towers of Hanoi puzzle.
Okay.
This is called the Cups of Hanoi, and I just made it up. You can never put a larger cup inside of a smaller cup, because if you did, you'd be a wizard. And you only have 3 places where you can set down the cups.
Okay, so the idea is to transfer the whole thing over. Is that right?
Yeah, to Adam's side, with only 1 place in the middle to kind of like be the interim place for cups to go.
Sure. So let's do our thinking process out loud here. Okay. So all of our cups here, it's like our cups are arranged like Russian dolls, a smaller one inside of a smaller one, and one of those things.
I think there's a shot glass inside of a whiskey glass, inside of a water glass, inside of a solo cup.
Yep. Yeah, the solo cup is the big one here. Interesting. Now, I wonder, is the solo cup actually bigger than this? Like, I don't know.
It's taller. Yeah. I couldn't find 4 cups that are strictly bigger.
Jeez, you fail, or I fail for not having enough cups. Okay, so we basically, the first option, we only have 2 options here. We're required to use the smallest cup first, and either we put it in front of you or in front of me. So Adam, do you have a strong feeling for whether I should put this the shot glass in front of you or in the middle here?
Honestly, I don't have a strong feeling about that. I'm not sure how much it would matter, but it probably matters, doesn't it?
I'm sure. Well, yeah, that's part of the strategy.
Oh, it totally matters.
Yeah, because then alternatively, so I guess in the interest of time, we're gonna just do it, right?
Okay, yeah.
Okay.
I would assume in the middle.
Okay, in the middle it is, which means that the next cup we have no choice.
Yeah,
we have to move this cup over.
So let me just, I'll do a play-by-play update. Yeah. Right now, the shot glass is in the middle of Adam, and all the other cups, the big, middle, and small cups, are in front of Gabriel.
Okay. So the next one, we have no choice. So now we've got the whiskey glass in front of Adam, and now we do have a choice. We can either put the smaller cup in the cup in front of Adam, or we can put... That's really all we can do. We don't have a choice.
We've got one choice here.
Okay.
Yeah, so there's not, in the first part of the game, you can see there's not very many choices.
Yes.
Yeah, definitely.
So now the whiskey glass contains the shot glass.
Yes.
Okay,
and there's only one thing that can be done. Now the medium-sized glass is in the middle of the 2 of them.
Okay,
all right.
This is starting to make sense.
Yeah, so, and I've had no choice about what I do yet because I don't have anywhere available. So we're almost done here. Now... Oh, guess what? This final choice here, I have all of the cups.
Oops, you did an illegal move just there.
What did I do?
I forgot to mention one rule. You're only allowed to move 1 cup at a time. You can't move stacks of cups.
Okay, well, we can still do this if we move the small one into the biggest and then this one into that one.
I forgot that we could move the small cup into the biggest cup completely.
Can we do that?
Yo, totally, yeah.
Okay, do it.
Okay, here we go. So this guy goes in here.
So the shot glass is in the solo cup.
Meanwhile, beads of sweat are starting to appear on my forehead.
And then the medium
pressure's
glass can go in here.
Good. Can we get a
now the medium glass is in the whiskey glass is in the medium glass in the middle.
Can we get like a golf clap? Oh. Okay. Like a sound effects. Okay. Now, 1 glass at a time. Should I move the tiny glass into the middle? Okay.
I believe so.
Now, I know our listeners probably have lost track, so
Oh yeah, but if you're at home doing this, you could just try it at home with 4 things of increasing size. Yeah. All right, so hold up, bud. The solo cup is in front of Adam. I just had to make sure the listeners knew what was going on.
I'm not too sure about this.
I'm sure, but our listeners are on the edge of their seat.
Well, just keep going.
Messed up somewhere. I'm not sure if we can do this. Can we do this? I don't think we can.
Yeah.
Can we?
We'll keep going.
We can. Okay. 6.
The whiskey glass is in the solo cup.
Yes.
Okay, and then. Yeah, we could put the shot glass in the middle glass, I guess.
Yeah, we don't have any other choice. Or that glass in here.
Yeah.
Okay. So I don't know now. At what point are we gonna stick a fork in this and call it down?
Oh wait, I'll trust me. I'm looking for certain things.
Okay.
It's getting a little bit more
All right,
confusing than I thought
now
it
it's
was
whiskey
gonna be.
glass on Gabriel's side, shot and medium-sized glass in the middle, and solo cup on the right.
Well, Gabriel is scratching his chin pensively. What's he gonna do? Okay.
I think so.
Okay. Shot glass in the whiskey glass.
All right. Water glass
In
in the solo cup.
Right.
We're almost there.
we are.
So now the medium glass is in the solo cup, and the shot glass is in the whiskey glass, and they're on opposite sides.
Okay. So obviously we have to do this.
Now the
There we go.
now the shot glass is in the middle.
Okay, and then whiskey glass in the medium glass. We're almost there. We got one move left.
Whoa! I didn't think we were gonna do it.
We did it.
Okay.
Now you notice that you had 4 glasses there, but it took quite a long time.
It took
Yeah.
quite a
Don't
lot.
I get another golf clap or something? I mean, I don't know, some sound
Absolutely.
effect. Yeah, but you have to add the
I think you just added it. I'll just double your voice.
Okay, yay.
Now I noticed that you guys were freewheeling it a few times. You're just kind of doing like things that did seem to work out at the end.
It only appeared that we were freewheeling it.
It was all calculated.
Well, let me show you an easier way of doing the puzzle.
Okay.
All right, let's see.
Okay.
All right, put all the cups back on Gabriel's side.
Okay, here we go.
Now what we're gonna do is now all I want you to do is take out the tiniest 2 cups and put them on Gabriel's side.
On Gabriel's side? Okay.
Just the tiniest 2. We're gonna reduce the puzzle to only 2 cups.
Okay.
Now move the cups to get it to Adam's side with the same rules.
Sure.
Just the 2 cups.
So 1.
Whiskey glass goes in the middle. I'm not. The shot glass goes in the middle.
Okay.
Whiskey glass goes on the right. Shot glass goes on the whiskey glass.
There we go.
That was easy, right?
3 moves.
2 cups.
Now, if you instead of considering that as being now remember the moves again. Were small glass in the middle, then big glass to the target square, then small glass in the big glass.
Okay.
Think about it this way: you start by moving all of the glasses in the big glass to the middle, then you move the one big glass to the right square, then you move all of them from the middle to there.
Okay. I'm
So
starting to sense an algorithm here.
You divide and conquer.
Yeah, divide and conquer.
So basically, stack all the 4 cups together again.
All right.
Okay. Or you take the modulus and conquer, right?
Listen to episode 35. Please be discreet.
Okay.
Now, your first task, obviously, is to move all 3 cups from the big cup to the middle one.
Okay. So
the middle square.
We're gonna start by moving the smallest cup all the way over, right?
Well, first of all, if the first task is to move all 3 to the middle,
Yeah.
now let's take that task as one task.
Oh, got it. I see.
Now, if you want to move 3 glasses to the middle, how do you move 3 glasses to the middle? Ignore the big glass.
I got this. I'm going to move the shot glass into the middle, and then I'm going to put the next glass over on the far right. And then I'm going to stack the small cup in Gideon's cup. And then I'm going to put the big cup in the middle.
There we go.
And then I'm going to move the smaller cup and the smallest cup, the Russian doll thing here, into the middle. So now all 3 are in the middle.
Yeah, but you move 2 glasses at the same time. But you can see how that could be done in 3 moves, right?
Did I move 2 cups? Oh, yeah. I just would have to do one after the other there. So
Yeah, you'd have to move the small cup to the shot glass to the solo cup.
Okay.
Then do all that. But basically, you just did 3 moves in
I
one.
cheated. Hang on. Yeah. I'll do it right here. Just so that we know that I'm not a cheater. Okay. There. Okay.
And of course, and now you move the shot glass to the middle.
Yes.
And look, you're on step 2 of the algorithm. You just move 3 from 1 to the middle.
Yay.
So the next step is obvious, right? Move the big one.
Okay. Cool. Okay.
I feel like we did a lot of extra steps when we did this the first time.
Yeah.
Yeah. So now you got to move. Now the next step is to move the 3 glasses in the middle to the one on the right, right?
Yep.
So how do you move the 2 in the middle to the one on Gabriel's side? Because remember, that's the middle step.
I would put the tiny shot glass in the solo cup.
Yep.
Okay. Cool. Yay. And then I would move the whiskey glass over here, and then I'd move the tiny glass
To the whiskey glass.
yeah. Or would I? Do we? No, we don't. Oh, yeah. And then we put this one in here.
Yep.
Cool. There.
And then the last 3 steps are obvious.
Yeah. 1, 2, 3. I love that sound. Don't you guys love that sound for our listeners? That's a great sound. Oh, yeah.
Now, what's interesting about this is that it's proven that this takes exponential time. And the kind of algorithm we just use is called a recursive one. But if we had 64 cups, for example, this would take much longer than the universe has been around to do.
Oh, wow. Jeez. That's a whole lot of cup moving. Wow. We aced that, dude. High five.
Yeah, we did this.
Yeah. What else you got for us? What else you got?
Large numbers.
That's it? Just large numbers?
Yeah. Like 30.
That's pretty large. Whoa!
Imagine having 30 houses. It is a large number.
That's a large number of houses.
Yeah, exactly.
But a number that's actually larger than 30, you'd probably agree is 100, right?
I would agree. I would
Yes.
agree with that, yes.
Yes.
And that only has 2 zeros after it. And as many of you know, Google, Googol, has how many zeros after it?
100?
Yeah.
100 zeros? Okay, that's what a Google is?
What about what number has a Google zeros?
That is called a Googleplex.
Googleplex.
I didn't know that.
Yeah, it's next on our outline.
Yeah. Like every 8th grader's like, yeah, I knew that. So,
God,
the ever powerful comeback. So,
you don't even know me. But Google is already so big that it's more than the number of particles in the universe, probably. Or I think it's like maybe 1,000,000 times less or something.
a little hand wavy, but okay.
It's around there. Yeah. But this is, imagine we took every particle in the universe and turned it into a zero and then made a new number of it. That would be gigantic.
That's
Wow.
pretty gigantic. Like, there's just no reference for that.
That's unfathomably huge. Dude, this is going to cause an existential crisis among all of our listeners who are trying to fathom that.
Well, keep your therapist handy because we're going to talk about Graham's number.
Okay.
Oh.
Okay, so basically this is how it's stated on Wikipedia, and then we'll do it in English. Connect each pair of geometric vertices on an n-dimensional hypercube to obtain a complete graph on 2 to the n vertices. Color the edges of this graph either red or blue. What is the smallest value for n for which every such coloring contains at least one single colored complete subgraph on 4 coplanar vertices? And this is just part of Ramsey theory, which is saying, like, I have a shape. How big does the shape have to be for this thing to hold?
That's the definition of Graham's number?
No, Ramsey. Well, that's the definition of Graham's number is the thing I read at the first part, and I'm going to simplify that real now.
Can you read that in Gordon Ramsay's voice?
Connect each pair of geometric vertices on an n-dimensional hypercube to connect a complete graph.
That was funny.
But what that means is a hypercube is like you take 2 cubes and you connect the corresponding vertices. That's a 4-dimensional cube. You do it with 2 4-dimensional cubes. It's a 5-dimensional cube, etc. That's a hypercube. We have an app on our website, breakingmathpodcast.com/hypercube.html. And basically what this is saying is how many dimensions...
Sorry, to answer your question, yeah, that app is a Hypercube app, which we've mentioned before.
Yeah. And so it's saying, like, if we have a hypercube where you connect every corner to every other corner, so like if we were a 3 cube, just a normal cube, it would be like all the corners are connected to all the corners, all the edges are there.
Okay.
But so like let's say we did this with like a 100-dimensional cube or something, some big dimension, and you're asking the question, how many dimensions does this have to be in, so that if we colored every line that we drew red or blue, would there be anywhere a square with an X in it where the square is red or the square is blue? And it turns out that the number of dimensions is very huge. That is the lower bound for the number of dimensions.
Oh, wow. Okay.
And we're going to have to talk about 2 things to actually talk about how gigantic this huge number is. So addition is, there's just, I don't know, what, like 2 plus 3 is what?
Yeah, 5, obviously.
Yeah.
I got that.
I agree.
And so 2 times 3 would be a repeated addition, right? 2 plus 2 plus 2, right?
Yes.
And then 2 cubed, 2 to the 3, would be 2 times 2 times 2, right?
Yes.
Yeah.
Which would be basically repeated multiplication, which in multiplication itself is repeated addition.
Yep.
And so exponentiation is repeated multiplication is repeated addition. But what is beyond exponentiation?
Repeated exponentiation.
Yeah, and then repeated that.
Interesting.
So imagine if you have 4 up arrows. So that's this is called Knuth's up arrow notation. So 1 up arrow is exponentiation. 2 up arrows is 1 step beyond exponentiation. So 4 up arrows is 3 steps beyond exponentiation.
Oh, wow.
So you could imagine 3 with 4 up arrows, 3 would be a gigantic number, right?
Yeah, that would add up pretty fast.
It would be like gigantic. It would be much bigger than Google, right?
Yes.
Wow.
That's step 1. Step 2 is to take 3, 4 up arrows, 3, and then draw that many up arrows between 3 and 3, and that's step 2.
Okay, so this is
wow.
what's beyond exponentiation of exponentiation.
Yeah. Now imagine you did that 64 times.
Good God.
Okay.
That's Graham's number.
So can we like make a bigger number for breaking math? Like
Do it 65 times.
Oh,
Just to be
God.
jerks.
Breaking Math's number.
You heard it first. Breaking Math's number is 4 with 5 up arrows to the 4 if n equals 1. But then 4 to the that many up arrows 4 65 times. It's bigger than Graham's number.
Yeah, take that, Graham.
Oh, geez, sorry. That's the kid.
Take that, Graham, and your crackers.
Yep. Wow. And why was Graham wanting to do this?
Oh, that's how many dimensions the cube would have to have
Okay.
to satisfy that property.
That's right.
Man.
I'm pretty sure that they think that the real number of dimensions is around 6 or something. But it could be as high as that.
That's
Wow.
that would be a lot of
It
dimensions.
would take the
That's-
count a long time to get that far.
It would.
Google.
A Google in one.
Especially if he has to laugh between each one.
Fortunately, he's immortal. It's a vampire.
Maybe that's what he does. He's immortal, so he just counts. How long would it take to count to Google?
I don't know, like a Google seconds.
Oh, that's it. Sorry, that wasn't a good math problem. My bad. Assuming that each laugh, is okay.
Sanity and awareness are forsaken in favor of the black mathematical arts. As you go forth, shame the unbelievers of the gravity of math by forcing them to move about 64 rings from one tower to the other with not any ring on top of another that is smaller than it. Tremble. Fear it. Fear it. I'm Mbaka,
And I'm Gabriel.
and this has been Breaking Math. On this episode, we had Adam. And Adam, anything you want to plug?
No, not really. Just glad to be here with you guys.
Awesome. Very good.
And any plugs that we got?
Yeah, I had mentioned earlier, actually, that we are about to launch a brand new podcast. We are teaming
Sorry, I
up.
cracked my knuckles as you were saying that.
Okay. Yeah, I'd like to mention. I had mentioned this earlier that we are about to launch a brand new podcast in which we had in which we had partnered with a local speech and debate coach. It's going to be a podcast all about speech and debate. It's going to have stories of great victories and horrible defeats, and about the art of arguing in communication. We are very excited about it. The podcast is called The Soapbox with Trey Smith. You guys should find it on Facebook. We have a lot of updates on Facebook. There's also on Twitter, which is at SoapboxPod1 on Twitter. And on Anchor, it's going to be anchor.fm/thesoapboxpod. So I'm very excited about it, and I'm glad that Breaking Math is finally spawning a new show.
Hooray!
And I think that's all I have for this episode.
Yep, and that's all I have for it too. Everyone, please enjoy math, and please ignore us unless you listen. And now, in honor of the new Planck constant, we have a song from Photon Rent.
6.626070158 to the negative 34 second. That is the quantum action. 6.626070158 to the negative 34 second. How do you measure the energy of a photon?
When you need mealtime inspiration, it's worth shopping Baker's, where you'll find over 30,000 mouth-watering choices that excite your inner foodie. And no matter what tasty choice you make, you'll enjoy our everyday low prices, plus extra ways to save, like digital coupons worth over $600 each week. You can also save up to $1 off per gallon at the pump with fuel points. More savings and more inspiring flavors make shopping Baker's worth it every time. Baker's, fresh for everyone. Fuel restrictions apply.